we will one day venture to the stars. So here we are on the path of human progress, dangers behind and dangers ahead. But on the branch leading to a good outcome, terraforming has long been seen as a good thing. So why terraform? Why turn a dead planet into a living one? We're all in a bubble of life that is limited in time and limited in space. Longevity research tries to extend that bubble in time, and terraforming research extends it in space. For any given level of technology, there is a planetary carrying capacity. The more planets, the more human numbers can be. For many, extending life beyond Earth offers protection against existential threats, protection for our biosphere, for our consciousness. And if we're going to expand into the galaxy, we'll need base camps for our exploration. On the scale of a galaxy, a base camp is a habitable planet. Mars once was a warm world with rivers, lakes, seas, oceans, but now it is extremely cold. And that low temperature is the zeroth order barrier to creating a photosynthetic biosphere on Mars. And in the talk today, I will focus on that first step, warming Mars to allow a photosynthetic biosphere. Timescale for that, decades. Later steps, once photosynthesis gets going, raising the oxygen level, have a much longer timescale of at least centuries, unless you are willing to confine the oxygen to domed habitats, or you are willing to raise the oxygen level to allow plants and trees on the surface, but not high enough for us to breathe. I lead a small team working on nanoparticles for warming Mars. Our latest paper, lead authored by Samena Ansari, shows that nanoparticles are at least 5,000 times more mass effective than the best greenhouse gases at warming Mars. I say at least because the particles we're looking at are very simple, just conductive 9-micron long rods. These resonate with upwelling thermal infrared, but allow the sunlight down to the surface. These rods are so light, much lighter than natural Mars dust, that like natural Mars dust, they're carried up by the winds and stirred globally, and that allows near-surface release. If you want to have melt on Mars, you need to raise the temperature above 273 Kelvin in the places that have ground ice, shown in tinted in white here. And you can do that with 160 milligrams per meter squared of that simple nanoparticle design I just described. We are looking at other designs. The particles do settle out, and so you need to keep resupplying them. And that means that the warming is reversible and controllable, and the nanoparticles can be engineered to be biocompatible and to degrade naturally. So how does this actually work? The red curve shows sunlight as a function of wavelength, and the blue curve shows Mars thermal infrared. And the panel at the bottom shows how strongly the nanoparticles interact with light as a function of wavelength. And as you can see, the nanorods interact about 100 times more strongly than natural Mars dust per particle in the thermal infrared range. But these nanorods are much, much lighter than natural Mars dust. We are investigating other particle types. Graphene nanodiscs, it turns out, that are less than 1 micron in size resonate beautifully with 20 micron thermal infrared. So if you can make these particles on the Mars surface, then you can do this. But this requires a particle producing system, a terraforming engine, to be transported to the surface of Mars. SpaceX has launched its Mars rocket, Starship, 4 times already, and in April, SpaceX released its Mars plan, which is to transport 250,000 tons to Mars every 26 months. SpaceX has almost completed building a factory, shown here, whose purpose is to build a Starship, a reusable Starship, every 2 days. Now, I don't know if SpaceX will actually achieve these numbers, but they are much, much more than are needed to transport a terraforming engine to Mars. So we can do this. So this idea appears to be on the critical path to terraforming Mars and perhaps human expansion into the galaxy. That statement I just made depends on a bunch of assumptions, and testing those assumptions is the goal of our near-term research. We need to expand our simulations to include more mass-effective particles. We've started doing that. And we've also started weather modeling for the deployment plume. We need more global modeling for the climate feedbacks. Moving to batch manufacture and lab test, we need flow tube experiments to measure clumping parameters, wind tunnel experiments for reuptake of the particles, and also we need to validate the radiative properties. All of that is funding constrained, but that will enable a precursor mission to Mars with a single spacecraft, release a plume, measure the warming. If that looks good, agrees with models, the next step is to raise Mars's global temperature by 10 Kelvin. Still much too cold to melt the ice. That would take, depending on whether you use solar power or not, dozens of Starship landings. Then check the climate feedbacks. If they look good, proceed to full deployment to melt the ice. Okay, so if you do that, you still have a very challenging environment for microbial life, which must deal simultaneously with the challenges of low pressure, low temperature, ultraviolet, perchlorates, and salty soil. And so that will probably require synthetic biology. A new FRO, Pioneer Labs, motivated by terraforming, was founded this year to engineer microbes for Mars. In April, we held a terraforming workshop. If you want to read the proceedings, just Google Mars Terraforming Workshop Proceedings in quotes to bring together engineers and scientists of all types to hash out a research agenda for terraforming Mars. Long term, we know that we can build up the oxygen level with photosynthesis to one that would enable green plants and trees on the surface. But we don't know if Mars has enough volatiles to raise the oxygen level to one globally to one that is breathable by humans with Mars resources alone. And so, advocates of terraforming must be advocates of the scientific exploration of Mars. As another example, we know that Mars has enough water for lakes and seas, but we do not know if Mars has enough water for oceans. We need to look for water reservoirs deep underground, and if they exist, then we need to check if they have life in them, because any Mars life, well, the study of such life would have great benefits that would warrant robust protections for its habitat. So in summary, terraforming Mars is like descending a mountain. At the very highest altitudes, the coldest, most harsh state, only cyanobacteria can live. Then as you keep warming, descending the mountain, you create a state where lichen can live, and so on. Just in the last few months, there have been major advances in terraforming, both from space science perspective, climate science perspective, and biology as well. And the next steps for the nanoparticle warming method, what I'm working on, are batch manufacture and lab tests of nanoparticles, which is funding constraint, which would pave the way for building and flying a precursor single Starship mission, which wouldn't warm Mars that much, but would serve to show that you can warm Mars. And so I guess that's it.
Thank you.
So I think Chris McKay originally estimated with like 2 greenhouse gases, you could warm up Mars about 100 years, and then 100,000 years to oxygenate Mars. What do you reckon are the timelines for using nanoparticles?
So Chris McKay is one of the reviewers for our paper, which is in press and we published on 7th of August. I have preprints that I'd be happy to hand out. That was 30 years ago. A lot has happened since then. So on the bad side, we now know from radar mapping that the polar caps are not rich in carbon dioxide ice. So that runaway feedback cannot occur. So you get a positive feedback. Some CO2 is there and will get released under warming, but it's not enough for runaway warming. Okay. So the timescales are very quick because Mars has low thermal inertia, so it responds rapidly to radiative forcing. So it's an engineering question, not a science one. But a couple of decades for the warming. For the oxygenation, the 100% efficiency photosynthesis timescale to oxygenate Mars to the point where we can breathe is 60 years, but that's completely unrealistic because that's just from an energetic perspective. So many centuries is more realistic. And so the potential worry is whether or not Mars has enough volatiles to actually provide the atoms for breathability, which I mentioned. Okay. Yeah. Oh, yeah.
Okay, you're just starting. Okay, I have a question. So I actually emailed you about this. Would this work on Earth? I would assume Earth has a different infrared spectrum from Mars and a much denser atmosphere. Also, the dynamics is different. So I would assume that the same nanorods will not have the same effect on Earth.
So you don't want to be releasing large...
I definitely don't want to increase that.
Yeah.
However,
I'm a Scandinavian, so I can kind of recognize the benefit of a warmer Earth.
The same basic principle works on Earth. So one way to build intuition for this is consider clouds and water vapor. So water vapor is a powerful greenhouse gas, but the mass, the column mass of water vapor greatly exceeds the column mass of cloud, and yet cloud and water vapor have roughly equivalent radiative forcings in Earth's radiative budget. So aerosols are very powerful. You would need a slightly different length of nanorod to tune it to Earth's thermal effect, but we don't want to be releasing these on Earth. Yeah.